Hello, everyone. Sorry for the delay. Welcome to this week's PNS on processing memory. I'm just going to double check if everything's working fine. Hello, everyone. Perfect. Sorry. Okay, so we are going to continue operations like addition, multiplication, division using the SIMDRAM substrate and using DRAM row copy and DRAM majority operations, right? Today, we are going to continue on that line. We are going to see the problems that that type of architecture has, and we are going to try to mitigate those problems one step at a time. So in particular, in today's lecture, I'm going to talk about this work that we published this year in HPCA called MIMDRAM, end-to-end processing using DRAM system for high throughput, energy efficiency, and program transparent multiple structure, multiple data computing. So before I start, I'm going to give a brief summary of what this work is about. So as we saw last week, process using DRAM architectures are quite efficient to alleviate data movement bottlenecks. And in particular, discuss processing using DRAM architectures, which utilizes the analog operating principles of DRAM cells themselves to do computation. So even though process using DRAM can offer performance and energy improvement compared to process-centric systems for data-intensive applications, they suffer from three excess granularity. So the first one is that they suffer from underutilization due to a mismatch in the data parallelism available within and across different applications. Second, map operation. So you have two vectors and you operate on top of those two vectors and you generate a third vector. But they don't support something like vector reduction operation. That you have one vector and then we reduce that vector into a scalar operand. This happens because there is no interconnect that connects different DRAM columns inside a DRAM chip at low cost. And third, they have a challenging programming model due to a lack of automation tools such as compilers to generate granularity. To this end, we propose MIMDRAM, which is a hardware-software co-design process using DRAM system. So the key idea of MIMDRAM is to leverage the fine-grained DRAM access and activation for process using DRAM operation. So that is the ability to only access only fragment of a DRAM row, doing a DRAM row access or an activation. So we leverage this key idea in both hardware and software. So in the hardware side, we implement simple modifications to the DRAM array to enable the allocation of only the resources required for a given process using DRAM operation. And this also allows MIMDRAM to concurrently execute independent process using DRAM operations in a single DRAM array. So we also implement DRAM peripheral logic, which allows us to implement native vector reduction operations. So on the software side, we implement compiler and operating system support to generate and map and we saw that it can significantly improve DRAM systems, high-end CPU and a GPU respectively, while incurring cost and DRAM chip costs as well. So this is the outline for the talk. I'm going to briefly give some background on DRAM. You probably are bored of this background already, but I'm going to try to be brief. So as you know, we provide this taxonomy some weeks ago. We have two main approaches of processing in memory architectures. processing near memory, which adds logic near the memory arrays for computation, or processing using memory, which uses the analog operating principles of the memory cells themselves to perform computation. And in this work, we are targeting processing using DRAM architectures, which use the DRAM, the analog operating principle of DRAM cells for computation. So before, as I start starting in the meat of the work, again, some briefly background on the DRAM hierarchy. So a DRAM chip is hierarchy organized. On the bottom level, we have a DRAM mat, which is a 2D array of DRAM cells. Rows in a DRAM mat shares a word line, and columns in the DRAM mat shares a bit line. Columns are connected to a set of local access amplifiers, and rows are connected to local row decoders. So multiple DRAM mats constitute a DRAM subarray. The many mats in the DRAM subarray are indexed using a global row decoder, which propagates the target row address across all of the mats using the global word line. To move data outside the DRAM mat, a DRAM subarray uses a global access amplifier. And to move data outside the DRAM subarray, a DRAM to execute two main DRAM, and on receiving activation, the global and local row decoder assesses the word line of the target row, connects the DRAM cells to the bit lines. Then, the system amplifier senses the perturbation caused in the bit line, amplifying and latching the data from the DRAM cells. Then the memory controller issues a read command to read a column of data from the previous latched DRAM row. So the read command moves the target DRAM column from the local system amplifiers to the global system amplifier, and finally to the memory channel via the I/O interface. So the operating principles of the DRAM cells can be used, as we saw in previous weeks, to implement move bitwise operations inside the DRAM chip. For example, row clone implements in-DRAM row copy operations by issuing back-to-back activations to the DRAM chip. So the first activate copies the source row into the local system amplifier, exactly as I mentioned before. And the second activate connects the destination which allows the previous latch source row to be written back to the destination row. Similarly, Ambit implements majority operations in DRAM by simultaneously activating 3 DRAM rows at the same time. So when we activate 3 DRAM rows at the same time, they simultaneously perturbate the bit line based on the DRAM cells content. So this allows the local system amplifier to amplify the voltage of the values stored in the DRAM cells. So what we saw in last week, we can use row clone in Ambit to implement more complex operations as provided by the SIMDRAM framework. So I'm going to show here how are those steps that we discussed last week for the SIMDRAM framework. Assuming that you want to compute a vector addition of two arrays, so array A and array B. Here, blue indicates a logic 1 and yellow indicates a logic 0. So we have So we saw last week, the first step of the SIMDRAM framework is to take a desired operation. So here I just have a simple RIP carry adder implemented using AND or and not logic gates. And then we use some equivalence to convert that AND or not based operation into a majority not only operation. And we optimize the circuit to reduce the number of triple activations that we need to perform for computation. Then in the second step, we traverse the majority inverted graph or majority not circuit, one gate at a time, generating a microprogram, and the majority operation inside the DRAM chip itself. We activate row A, B, and B the carry out row, and what the majority or the DRAM chip is computing is basically the majority of 1 and 0, which is equals to 1. Then we move to the next gate, which computes again the majority of A bar, B, and carry in and store the data in a temporary row. And here what you're going to have is the majority of 0, 1, and 0, which is equal to 0. Then we move to the third majority gate, which computes the majority of A and the two previous generated majority outputs, which is going to be the majority of 1, 0, and 0, which again is equals to 0. So in the end, we have in the carryout row a row filled with ones, and in the sum row a row filled with zeros. And then if you read this value, you're going to have 1, 0, which is equals to 2. So in the end, we got the result of our vector addition operation inside the DRAM chip itself. So if you pay attention to this example, see the processing using the DRAM chip basically as a very wide bit serial SIMD engine, single instruction multiple data, where we execute bit by bit of a data word. As I mentioned, the example was only 1 bit, and we have as many operands as we have DRAM rows inside the DRAM subarray, or as many SIMD lanes as we have in the DRAM subarray. So before this year or this work was mostly shelf-DRAM chips, and we saw the commodity of the shelf-DRAM chips are of performing Bitwise operations without any hardware modification. So we demonstrated in this work that we can simultaneously activate 48 DRAM rows in two neighboring DRAM subarrays. We can perform NOT operations with up to 32 output operands, and we can perform 16 input and NAND, OR, and NOR operations inside commodity of the shelf DRAM chips by violating DRAM timing parameters. So all of really good, but process using DRAM architecture suffers from three main limitations due to the large and rigid executionality of DRAM chips. So first, they suffer from SIMD utilization. Second, they suffer from a limited computation support. And third, they have a challenging programming model. So I'm going to elaborate on all of those limitations next. Starting with the SIMD utilization. So in order to understand the amount of data parallelism a process using DRAM architecture can leverage, we can't find the SIMD parallelism in real vectorization factor metric, which is the maximum number of scalar operands that fits into a SIMD register for a given looping application. So to achieve high SIMD utilization, the ideal maximum vectorization factor of a loop to match the number of DRAM columns in a DRAM subarray perfectly. So if it's larger but is not a multiple of the number of DRAM columns inside the DRAM chip, you're going to suffer from SIMD utilization as well. So in our application analysis, we collect the maximum vectorization factor of all vectorizable loops in 12 real-world applications, and we report their distribution using box plot, where whiskers extend to the maximum and minimum values and bubbles depict average values. So as a reference, any value above the green line represents high SIMD utilization for a process using the DRAM system. So we draw two. First, SIMD utilization, SIMD parallelism significantly varies within and across different applications. And second, only very few loops have enough data parallelism to achieve high SIMD utilization. So let's look next to the second issue. So process using DRAM architectures can only support parallel map operations. So unfortunately, limits the process using DRAM applicability since commonly used reduction operations cannot be implemented natively at low cost. Over here is there is a lack of direct communication path across the many DRAM columns in the DRAM subarray. And directly connecting all DRAM columns using custom fabric leads to large. Third, process using DRAM suffers from a challenging programming model. So currently, process using DRAM prototypes use assembly-like programming models, which leverage several key tests, leave several key steps for the programmers to handle manually. So I'm going to illustrate such tests with a simple predicated addition subtraction operation. So a programmer needs to map and align the data structures involving the computation respecting DRAM's organization, identifying the array boundaries of a target loop, and manually vectorize the target loop while working to feed as many data operands to the DRAM array as possible for high SIMD utilization, and manually orchestrate data movement across dependent operands. As a result, the produced process using DRAM code is often complicated and potentially inefficient. So to summarize, process using DRAM architectures suffers from rigid and inflexible access granularity of DRAM chips, which affects their applicability to different applications. Thus, our goal in this work is to design a flexible process using DRAM system that overcomes the three limitations caused by DRAM's large and rigid access granularity. So to this end, we propose MIMDRAM. So MIMDRAM key idea is to leverage fine-grained DRAM access for process using DRAM operation. So in traditional architectures, on every DRAM access, all rows in a DRAM matrix are asserted, even if only portions of that row is going to be for the access doing a cache, a column request. Since the global word line propagates across all of the DRAM matrix at the same time. DRAM architecture segments the global word line as individual DRAM matrix on a DRAM axis. So fine-grained DRAM architecture has been previously proposed for energy-efficient DRAM access, but here in the context of process using DRAM, fine-grained DRAM provides three main benefits. First, it improves SIM utilization for a single process using DRAM operation by accessing only the DRAM matrix with the target input operands. Also, we can leverage the unused DRAM matrix to concurrently execute independent process using DRAM operation in a multiple structure, multiple data execution model. Second, we can leverage the global and local databases that connects DRAM matrix to move data within and across DRAM matrix, allowing of vector reduction operations. Third, since the number of DRAM rows in a single DRAM matrix are on par with the number of SIM delays in vector instruction set architectures, we can ease process use DRAM programmability by leverage current compiler infrastructures for such instruction set architectures. So based on that, we propose MIMDRAM, a hardware software co-design process using DRAM architecture that enables fine-grained process using DRAM computation at low cost and low programming effort. So MIMDRAM constitutes of hardware and software components, which I'm going to elaborate next. Let's start with MIMDRAM's hardware overview. It started from its DRAM array modifications for fine-grained process using DRAM computation. So we modify a DRAM array circuitry with four main components. First, the isolation transistor segments the global word the current activation row for a MET, allowing the row decoder for a different row. The MET selector asserts the isolation transistors based on a MET range specified by the process using DRAM operation. So the MET range addresses a physical continuous set of DRAM METs. Next, let's talk about how to move data inside the MET. But before, I need to provide further background on a DRAM column access. So during a DRAM column access, data is locally and globally amplified to improve signal integrity. The data column is first in the local system amplifier, and then latch and amplify using helper flip-flops at the peripheral logic of the DRAM MET. Then the data is moved from the helper flip-flops into the global sense amplifiers. Our key idea to move data within a DRAM MET is to leverage leverage the local and global sense amplification paths already present in the DRAM MET and then the DRAM subarray. So first, we implement an inter-MET interconnect at the DRAM peripheral to move data across METs. This interconnect creates a path between adjacent global sense amplifiers. And this path allows us to move data across adjacent DRAM METs. We leverage the helper flip-flops in the DRAM MET to move data within a DRAM MET. First, we latch the destination columns without erasing the data previously latched in the helper flip-flop. This allows the helper flip-flops to drive the source column into the destination column. So we leverage the inter and inter-MET interconnects to implement in-DRAM vector reduction in 3 steps that implement a reduction tree. So let's assume that we want to sum all of the elements of 2 vectors into a single element. So we use 2 DRAM METs in this example. To do so, we first compute the target process using DRAM operator both data elements. Then we move the results of the first computation in the first DRAM MET to the second DRAM MET via the inter-MET network. Once the data from the first MET is in the second MET, we can once again compute the reduction step using only the second method. Finally, I'm going to briefly discuss our control unit design. So the goal of MIMDRAM control unit design is to implement, is to schedule and orchestrate the execution of multiple process using DRAM operations transparently from the user. To highlight three main components of our control unit. First, the method scheduler is responsible for identifying which process using DRAM operation can be dispatched based on the current method utilization. Second, the method scoreboard keeps track of the currently utilized methods. And the microprogram processing engines dispatch the DRAM access for a given running process using DRAM operation. Next, starting with our new compiler support for process operations. So transparently from the user, extract SIMD parallelism from application and schedule process using DRAM instructions while maximizing SIMD utilization. To this end, we implement three LLVM passes targeting process using DRAM execution. So the first pass is responsible for identifying SIMD parallelism in a code using LLVM auto-vectorization engine, generate process using DRAM instructions, and set the best vectorization factor for such process using DRAM instruction. The second pass is responsible for scheduling and mapping computation. Our pass uses metadata to mark independent process using DRAM instructions that should be executed concurrently across different DRAM methods. Finally, the third pass is responsible for code generation and data allocation for a process using DRAM instruction. Our compiler passes rely on the system support we implement for a process using DRAM instruction. Such as system support includes ISA extensions, execution and data transposition, data coherence, address translation, data location and alignment, and metadata translation. I'll briefly discuss our data location and alignment routine. So MIMDRAM requires data from process using DRAM instructions to map to the target DRAM method correctly. To allow the memory allocator to influence the physical data allocation of process using DRAM operations, we implement a new memory allocator that leverages huge pages and reverse engineer DRAM interleaving schemes or information for process memory objects. For more details, I invite you to check our paper. Next, I'm going to give a brief overview of our evaluation results. So we compare MIMDRAM to a high-end CPU and GPU, two state-of-the-art architecture. In our analysis, we use 12 workloads for 4 benchmark suites and 495 application mixes from search workloads. We perform a two-level analysis. First, for single applications, MIMDRAM can leverage its inter-application data parallelism, and for multiple applications, MIMDRAM leverages inter-application data parallelism. First, we evaluate the energy efficiency of the CPU, GPU, SIMDRAM, and MIMDRAM for 12 real-world applications using a single DRAM subarray, which is conservative for process using DRAM system. Values are normalized to the baseline CPU. So we observed that MIMDRAM significantly improved energy efficiency compared to the three baseline architectures. Next, we evaluate SIMDRAM throughput of MIMDRAM, evaluate this system throughput for MIMDRAM and SIMDRAM using the weighted speedup method. For fair, SIMDRAM using bank level parallelism so we observed that MIMDRAM improves system throughput using a single DRAM bank for computation compared to SIMDRAM using multiple DRAM banks for computation. Finally, we compare MIMDRAM to other processing memory architectures for our 12 applications. For fairness, we report performance normalized area results, since such processing in memory architectures incur significant area cost to the DRAM chip for computation. So we evaluate the performance of DRIZA, Fulcrum, and MIMDRAM, and values here are normalized to MIMDRAM. We observe that on average across all of the applications, MIMDRAM improves performance per area compared to both DRIZA and Fulcrum. We have many more results in our paper, including comparison to DRIZA and Fulcrum from multiple applications, SIMDRAM utilization versus MIMDRAM, MIMDRAM's performance with subarray and bank level parallelism, and our area analysis. For all of that, I invite you to check our paper. To conclude, in this paper, we propose MIMDRAM, a hardware-software co-design process using DRAM evaluate MIMDRAM, and we observed that significantly improved performance and energy efficiency and system throughput compared to processor-centric and memory-centric architectures while incurring small area overhead. So we hope and believe that MIMDRAM's idea and results will help to enable more efficient and easy to program process using the DRAM system. So this was MIMDRAM. I don't know if there's any question from Zoom. Okay, I don't think so. So thank you so much for listening. Next week, we are going to discuss something that I briefly mentioned here, which is how we can do those book bitwise operations in commodity off-the-shelf DRAM chips. So we are going to have different presenter. So Ismail, in case you're bored of me talking about process memory, you're going to have some refreshing faces next week. So again, thank you so much for your time and attention, and I see you next week.